Now live.
Good evening, everyone. Welcome to the Ramanujan Colloquium, which is being held in commemoration of the great Srinivasa Ramanujan's birth anniversary. And today we have two lectures scheduled, and the celebration continues tomorrow with two more lectures, which also includes this year's most awaited lecture from our Shastra Ramanujan winner, Professor Will Savin. Today's sessions, as well as tomorrow's, are being chaired by Professor Alladi Krishnaswamy, who's been a champion for spreading the Ramanujan's legacy. He has himself a long and illustrious career, and for the benefit of the young students who are tuning in, I would just like to give about a very brief introduction about this illustrious person who's chairing today's session. Professor Krishnaswamy Alladi is an alumnus of Madras University, where he completed his BSc and later on went to do his MA and his PhD from the University of California, Los Angeles, where his mentor was the legendary E.G. Strauss. And he has a rich professional experience, and currently he is a professor in the Department of Mathematics, University of Florida at Gainesville. He has won numerous awards and has received so many grants for carrying out research on his areas of interest, which is number theory, analytical number theory, sieve methods, probabilistic number theory, Diophantine approximations, partitions, and Q-series identities. I can go on and on, but in the interest of time, I would like to stop here and would like to welcome Professor Alladi Krishnaswamy. And today we are going to have two wonderful speakers who are going to touch upon different facets of the research inspired by Srinivasa Ramanujan. I welcome them, as well as today's this year's winner of the Shastra Ramanujan Award, Professor Will Savin, to this event. Welcome to all of you. And I would like to hand over the session to Professor Krishnaswamy Alladi. But before that, I have a word about how the speech is and the interactions are scheduled. So all of you will be watching in YouTube the lectures. I request you to post your queries in the chat box. After each lecture, we have about 10 minutes when the speaker would interact with you and answer your queries. And I would like you to post any inputs, any comments also on the chat box, so that could be actually transferred to the speaker. So thank you. And over to Professor Krishnaswamy Alladi to chair the session.
Thank you, Uma, for your kind words about me, which I actually did not expect. I'm not a speaker, but anyway, thanks. This is the second year that the Shastra conference is being held virtually, again, in the interests of health issues and so on. So we need to be cautious for international travel. But I do appreciate Shastra taking the initiative to do this conference. Also, we are very fortunate to have four very distinguished speakers over this two-day period, including, of course, the winner of the Shastra Prize this year, Professor Will Savin. I will be introducing, of course, each of the speakers during the talk. And the first talk today is by Professor Philip Michel. And let me just say a few words briefly about him. He is a very eminent number theorist, specializing in analytic number theory, but I want to emphasize modern analytic number theory, in the sense that his number theory not only has its roots in the classical origins of the subject, but has interactions with algebraic geometry, and in fact, more recently, even with ergodic theory and quite a bit of algebraic number theory as well. So he is working in modern analytic number theory, which actually will be the subject of his talk. He is a professor at the École Polytechnique Fédérale Lausanne in Switzerland, and he had received his PhD from the University of Paris in 1995. He actually has a major collaboration going with Professor Will Savin, our Shastra Ramanujan Prize winner. In today's talk, he is actually going to discuss the idea of congruences, which goes back really to Gauss in a very fundamental form, which actually deals with division and remainder. But this very simple rudimentary idea of the algebra of remainders has now been very broadly generalized and being discussed in depth in the context of algebraic number theory. So that is what Professor Michel is going to focus on in his talk. And the title of his talk is Congruences in Modern Analytic Number Theory. I now request Professor Michel to give his talk.
Okay, so thank you very much, Krishna. I'm very happy to give this talk in honor of Will Prize, Will Sastra Ramanujan Prize. So I will start to share my screen, maybe, if I can do it. Okay, do you see something? Ah, yeah, okay.
Yes, we do now.
Okay, okay. So my talk is, as Krishna said, is about congruence in modern analytic number theory, and it's with a focus of what we like to call the applied L-adic cohomology. So a kind of a strange strange title, a bit ambiguous and contradictory, but so let's see what this is about. And so first, I start with a picture of Will, which maybe is not so recent, but I think it's more or less from the time that I met him. And so what I want to explain is precisely the line of ideas that I have led to this collaboration with Will. Okay, so this line of ideas, in fact, it came from joint work and still ongoing work with Etienne Fouvry, who was my PhD advisor, who is here, and Emmanuel Kowalski, my very long-term collaborator. And so I will explain what we were doing and in the end, how we'll enter the game. So, as Krishna says, the talk is really about the notion of congruences, which were really put to light by Gauss, formalized by Gauss. It existed before, of course, but he was, I think, the first to put a true name on congruences. So this is an issue of the bulletin of the American Mathematical Society about the work of Gauss, and especially I will be focusing on the disquisitiones, where the concept of congruence was really presented. So I recall you that notion of congruence is if you give yourself some non-zero integer, the modulus, and then you say that two integers are in the same congruence class modulo q if their difference is divisible by q, and this is an equivalence relation, and you write this to notice that two integers are connected via this relation, and it means just that one of the integers belongs to the congruence class defined by the other, which is the set of translates of the group QZ of multiple of Q by N. And so this is essential in number theory, but especially in analytic number theory. And what one wants to do in analytic number theory is how this notion of congruence interacts with other naturally defined arithmetic functions, which are just functions defined over the integers. When you, so what do I mean by interaction? One takes an arithmetic function and one wants to evaluate how it behaves upon restriction to a given congruence class or a set of congruence classes. And so I recall you, so this is elementary arithmetic, but I assume that not everybody is a number theorist. So in the beginning, I will just develop this notion from ground. So the set of congruence class is noted usually Z mod QZ. And so this set has a structure of commutative ring, for which the natural projection, which to an integer associate its congruence class, is a ring morphism. Also, you know that by the Chinese remainder theorem that this ring decomposes into a product of congruence rings according to the decomposition of the modulus into prime powers, into product of prime powers. And so when studying congruence modulo an integer q, this reduces the problem to studying congruences modulo power of a prime number. And eventually, the most interesting case very often is when this prime power is just a single prime. And so in most of this talk, I will assume that I will consider congruences of modulo an integer q, where q is a prime. And so then the ring of congruence classes is noted fq, and in fact, this is a finite field of cardinality q. So the modulus won't always be a prime, but very often it will be. And so why are congruences that important? So because, for instance, one application is that you can use them to study a Diophantine equation. These are the set of solution of a polynomial equation. So P is a polynomial whose coefficients are in the integers. So you want to study the set of roots of this polynomial, and you want to look for the solution which are integers. And when you have, so the notion of congruence gives you a necessary condition for existence of such solution, because if you have a root, a set of roots, or a solution to this polynomial equation, and if you reduce it modulo any integer q, it gives you a polynomial solution, a similar polynomial solution, but in the congruence ring, Z mod QZ. And this ring is finite, so it's relatively easy to study this set of congruences. And but this is just a necessary solution. So in particular, if for some modulus your set of congruent solution has no solution, then this implies that you have no solution over the integers. And this is a powerful criterion. But when this condition, necessary condition, is also sufficient, this has a name, and this is called the local global principle, or also the Hasse principle, after Helmut Hasse, who developed this, studied this notion of local to global principle in great generality, and some also other mathematicians before him. And then anyway, when you have this necessary and sufficient condition, you want to study the set of polynomial solution in this congruence ring. So, okay, an example where the local global principle hold is for quadratic forms. And you know from Fermat the sum of two square theorem. You know also from Lagrange the sum of four square theorem. And there is also a sum of three square theorem, which is due to Gauss and Legendre. So this theorem says that an integer is a sum, can be written as a sum of 3 squares. So meaning that this polynomial equation has a solution in integers, if and only if the integer is non-negative. This is obvious. And the integer is not a power of 4 times an integer congruent to 7 mod 8. So you see the notion of congruence occurring. And this is really a necessary and sufficient condition, so a form of Hasse principle. And so this theorem was proven by Gauss in the Disquisitiones using congruences and the law of quadratic reciprocity. But 3 years before Gauss, Legendre had given a proof. So, but there is a caveat. This Legendre proof was not complete. What Legendre used in his proof as really a key ingredient is he assumed true a result which would be proven only 40 years later by Dirichlet. And this result is called the theorem on primes in arithmetic progression. It says that if you give yourself a modulus and a congruence class, so A, which is a coprime to this modulus, then you can find infinitely many prime numbers which belong to this congruence class. And so again, Legendre took this for true, but this was not proven at the time of Legendre. So, and so this theorem of Dirichlet is one of very important theorem in analytic number theory, but also in number theory in general. And okay, and so Dirichlet proof was analytic and was modeled in a way on Euler proof that there are infinitely many prime numbers. So for this, Euler used the properties of the zeta function over the real line. And so Dirichlet kind of so used Euler proof as inspiration, but he had to introduce new ideas and concepts, and in particular, he introduced the notion of Dirichlet character of modulus Q. And the Dirichlet character is a group homomorphism of on the multiplicative group of the ring, of the congruence ring, we value into the multiplicative group of the complex numbers, so necessarily complex number of modulus 1. And this set of characters as a group structure for multiplication, with the neutral element being the constant function equal to 1. And the order of this finite group is equal to the Euler totient function. So why is this group, what is this set of Dirichlet character important to find primes in arithmetic progressions? So this is because it gives a kind of analytic way to detect, or at least an alternative way to detect whether an integer is in a given congruence class. So because you have this formula that the characteristic function of a congruence class, A mod Q, is given by an average over the Dirichlet characters, the value at the integer of the Dirichlet character. And in particular, if you want to count the prime numbers in arithmetic progression, you can use this formula to decompose this sum, which you would like to prove is becomes infinite when the variable x goes to infinity, into a sum involving this non-negative term, which counts the prime numbers, and this sum over Dirichlet characters, which are not trivial. Okay, and it's a sum over Dirichlet characters evaluated at prime numbers, and this is this thing that one wants to evaluate, and in fact to show that it is small. So Dirichlet did it for a variant of this sum, but here it just displays the most natural sum that that one would like to study. Okay, and so then Dirichlet, to any such Dirichlet character, Dirichlet associated so-called Dirichlet series, which in fact is an L function which mimics the zeta function. And in particular, it has a Euler factorization formula. It decomposes as an infinite product along the prime numbers. And then the proof of Dirichlet theorem reduced to checking the analytic properties of this Dirichlet L function. And the key result regarding the analytic properties is following non-vanishing result that any non-trivial any L function associated to a non-trivial Dirichlet character does not vanish at the point 1, s equal to 1. Okay, and so Dirichlet proved this non-vanishing result using what was called his class number formula. So by showing essentially that the product of value at 1 over all these Dirichlet characters was equal to proportional to a group, and the group has at least one element, so the product cannot be 0. Okay, and now we can, with Dirichlet theorem, we would like to go further and look for a more refined result. And if you want more refined result on prime in an arithmetic progression, you will need more refined analytic property for this Dirichlet L function. And building, using the work of Adamar de la Vallée-Poussin regarding Riemann zeta function, Landau, Edmund Landau extended the work of Adamar de la Vallée-Poussin and proved a more precise version of Dirichlet theorem. But if you count the number of primes less than x in a given arithmetic progression, then this number is equivalent to x over log x time a multiplicative constant, which is the inverse of the size of the multiplicative group of congruences when x goes to infinity. So it shows that you have infinitely many primes in a given arithmetic progression. In fact, Landau result was a bit stronger. And again, so Landau proof is a consequence of, again, of non-vanishing result for this Dirichlet function, that this Dirichlet function does not vanish, not only at s equal to 1, but on the whole complex line, real part of s equal to 1. So just make a small drawing. So you have, oh, okay, it erases itself. Maybe I can write it here. So you have the complex plane here. Here you have s equal to 1. And so Dirichlet proved, Landau proved that, in fact, the Dirichlet function, which is now viewed as a function of the complex variable, does not vanish along that line. Okay, and but in fact, now if you look for more refined question, and we will have more example in the next talk, I guess, then you not only you want to count prime number in arithmetic progression of some modulus, but you want to allow the modulus of the congruence class to vary with this variable x. And so this So you have a kind of more moving target theorem where you want to do this count, but in terms of x, but also when q is moving. And for instance, an example is a theorem of Carl Ludwig Siegel, which tells you that this formula, asymptotic formula of lambda O, remains true if the modulus is allowed to grow a little bit with x. So as long as q is less than some fixed but arbitrary power of log of x, then you have again this formula. So q could move with x, but very slightly. And again, this is a consequence of a more refined non-vanishing result, the part of which is due to Siegel. So yeah, maybe I could have put lambda O as well under the name of this theorem. So what is the best that you can hope for? So the best you can hope for is that you can assume the so-called generalized Riemann hypothesis that I will state. So what is the generalized Riemann hypothesis? It is the fact that these Dirichlet L function do not vanish when the complex variable has real parts strictly bigger than 1/2. So I will redo my drawing. So here this is 0. So before we were just looking for being non-zero at 1. This was Dirichlet. Then when we discussed lambda O, it was along the line real part of S equal to 1. But the generalized Riemann hypothesis postulates that there are no zeros at all in all this strip right on the right of this middle line called the critical line. And so if you assume this really major hypothesis, what you obtain is that this asymptotic formula holds as long as the modulus is a bit smaller than the square root of x. So it's a considerable improvement compared to Siegel theorem, which allowed a power of log x, and now you have a positive power of x instead. And moreover, this positive power is 1/2. And this is the best that you can hope for. And of course, this Riemann hypothesis, it's nearly untouchable for the moment. So maybe someone will prove it. I don't know. But for the purpose of working in analytic number theory, one is very fortunate that there exist substitutes to this conditional theorem which are unconditional. So, and this is maybe one of the most important is the so-called Bombier-Vinogradov theorem. It is from the 70s in the 20th century. And it says the following. It says that you take now the difference for the prime counting function minus the expected main term. So it's slightly modified. It's not exactly this term, but it's the integral logarithm that you should put instead. But let's just simplify. So you look at this difference of your prime counting function in arithmetic progression minus an expected main term. You take the maximum over all congruence classes mod Q. So, and then you average this error term over all modulus Q less than some big number Q. And what the theorem says is that on average, this average is rather small. It's as small as if you had, say, as if you have a really individual asymptotic formula. But what is very important is that this thing is true on average over modulus Q up to size square root of X. So the Bombier-Rivinogradov theorem, what it does for you is to give you an average substitute to the generalized Riemann hypothesis, but which is a true theorem. And in many instances of analytic number theory, you don't really need, you would be thrilled to have it, but sometimes you don't really need to have an exact formula for individual moduli, but sometimes only moduli on average are sufficient. And this theorem does as good as Riemann hypothesis. So it's a very important theorem. Bombier won the Fields Medal in part because of this theorem. And so here are some applications to this unconditional result. So an application is to the so-called twin prime conjecture, or called Polignac conjecture, that you are looking for whether there exist prime numbers such that the prime plus 2 is also a prime number. And the conjecture gives you an asymptotic formula, so a prime of that shape such that, a pair of two prime numbers P and of two prime numbers which are at distance 2 from one another, it's called a pair of twin primes because they are at the shortest possible distance. And so besides 2 and 3. And then if you count the number of twin primes less than x, or x plus 2, then you have a conjectural asymptotic formula. Now it's not x, it is not x over log x, but it is x over log x square up to a multiplicative constant, which is known. And using the Bombier-Rivinogradov theorem and so-called what is called sieve methods, so the Chinese mathematician Jingrun Chen proved that there exists infinitely many primes P, such that P plus 2 is either a prime or a product of two prime. So it's almost a prime and it has at most two prime factors. So it's quite close to being a twin prime because it does not have many prime factors. And in fact, Chen gave not an asymptotic formula, but a lower bound for the number of almost twin primes. And Chen proof used the Bombier-Rivinogradov theorem. So, I also want to discuss another deformation of this twin prime conjecture, or Polignac conjecture. So instead of looking at pairs of primes which are at distance 2 from one another, a simplification of the problem is to look at pair of primes which are at some distance of one another. So say at distance, not some distance, not at distance 1000, but at distance less than 1000. So it could be at distance 2 or at distance 4 or at distance 6. So you don't know, but if you take an interval of length 1000 and starting with a prime and you find another prime, then you are very close to having a twin prime. And you want to look for infinitely many of them. And then there is a fantastic result, very recent, in fact, of Goldstone, Pins, and Ildirim, which are pictured here, who proved, so they prove unconditional result, but for my purpose, I will discuss their conditional result. So suppose that in the Bombier-Rivinogradov theorem, the constraint square root of x, big Q less than square root of x suppose that you can replace it by BQ less than x to the 1/2 plus something, strictly positive, absolute. So suppose you can beat the bound in the Bombier-Rivinogradov theorem by some positive exponent. Then you can find bounded gaps between primes. So you can find an absolute constant, which would depend on this exponent, such that for infinitely many prime, this interval will contain two prime numbers. So the initial, the beginning of the interval and some other prime number. And but if you look at this theorem, if you think of the Bombier-Rivinogradov theorem, this looks like quite amazing, because here it says you would replace this 1/2 by 1/2 plus something, some eta, where eta, say, is 1/1 million, for instance. But this eta, 1/2 plus eta, being strictly bigger than 1/2, it means that you would have obtained a theorem that you cannot prove by a direct application of the generalized Riemann hypothesis. So it is expected to be quite a strong result, again, going beyond Riemann hypothesis. And what is quite amazing is that not very long after their breakthrough, Yitang Zhang was able to prove a form of the Bombier-Rivinogradov theorem going beyond the generalized Riemann hypothesis. So what you need to make a small compromise. So instead of summing over all possible moduli, you sum over all moduli which are smooth, which means that these are moduli which have a lot of small prime factors. So, which is one definition of smoothness. And if you restrict your average to these smooth moduli, then you can pass the exponent 1/2, the Bombier-Rivinogradov exponent, by a very small amount, so 1/500, something like this. But you can go beyond 1/2 and break the generalized Riemann hypothesis, kind of. And so this work of Zhang, so from a few years ago, it was in a continuation of works of Fouvry and Bombieri, Friedlander, and Ivaniek, who worked out some example version of Bombier-Rivinogradov passing this exponent 1/2. But these versions were not strong enough to apply this theorem of Goldstone, Pilz, and Hildering. And but even if Zhang's theorem had a compromise, restriction on smooth number, nevertheless it was sufficient to imply the consequence of the Goldstone, Pilz, Hildering theorem. And Zhang proved that there exists a constant, which I will call Z, such that infinitely many pairs of primes are at distance at most Z from one another. And so this constant Z, it has a really precise value. So this exponent 1/584 leads to a value of Zhang constant, which is 70 million. So this looks like a huge number, but this is a finite number, an absolute number. And so this is why the work of Zhang was so much shocking and was lauded when it appeared. So, shortly after, maybe some epilogue, shortly after the work of Zhang, people tried to improve this 70 million constant. And so it was the topic of a Polymath 8 project. And then polymath 8 was able to reduce this constant to 5,000, which is a significant improvement. And then shortly after the completion of the project, when it was declared finished, came James Maynard, who is also a winner of the Sastra Prize, and who provided a different approach to the initial argument of Goldstone, Pins, and Hildirim. And in fact, he proved that Zhang constant could be reduced to 600. And in fact, he did not need to beat the Bombier-Rivinogradov theorem. Only the initial Bombier-Rivinogradov theorem was sufficient, and in fact, even weaker forms of it. And okay, but then it was also another big surprise. And then Maynard joined the Polymath 8 project, and then the 600 was further reduced to this 246, and I think it is still the current record for gaps between primes, but maybe someone has done better, I don't know. Anyway, so, but all these stories for what is that if I go back to Zhang's original argument, who broke the Bombier-Rivinogradov theorem, really a fundamental aspect of his work was the use, indirect, but the use of method of Analytic cohomology and what I call trace function. And this is more or less the main topic of this talk. So, okay, so how does it go? And how does it connect so-called to modern analytic number theory, which is already very modern here? So what happens is that to prove the Bombier-Rivinogradov theorem, or even to break this 1/2 exponent, you use sieve methods and combinatorial identities. So one famous is due to Isbron, to write the prime detecting function into a much simpler arithmetic function, which are simpler, and these include the so-called generalized divisor function. So the generalized divisor function dk of n, if you give yourself an integer, this is the number of ways that you can write n as a product of k integers. So if k is equal to 2, this is just the number of divisor of n. And then you have this divisor function, and what you need to do is to study how this function is distributed in arithmetic progression. So you need to evaluate this sum of the divisor function along an arithmetic progression. And you would like, of course, the arithmetic progression to be the Q to be as big as possible compared to X. So what you can analyze this sum by writing explicitly this divisor function as the way of the number of ways of representing n as a product of k integers. And then you can transform this sum by applying the Poisson summation formula to each of these k factors. And then your sum becomes the sum of a main term plus a kind of a strange sum over integer in a different range of the same generalized divisor function, but not weighted by the characteristic function of an arithmetic progression, but weighted by this strange expression, which is an expression over powers of the congruence ring modulo Q. So you are summing over variable in this congruence ring of some function, which is an additive exponential modulo Q. And then, so this strange factor is summed against this divisor function. So this strange factor is called Napier-Klosterman sum, and then you need to be able to bound this average to say something. And so then I briefly return to the case, the original Klosterman sum. It corresponds to the case k equal 2, so the divisor function, but they occur in a different context. In fact, they occur in the work of Klosterman when he studies such a quadratic polynomial equation, so a generalization of Lagrange four-square theorem, whether you can represent n as in this as a polynomial of this shape of degree 2, homogeneous polynomial in 4 variables. Then using the so-called circle method or a variant of it, Klosterman made appear the original Klosterman sum, which is again the case where you have only 2 variables or corresponding to the divisor function. So this sum here is the sum of about q terms, which are all of modulus 1. So a trivial bound for this sum is square root of q. And this was not sufficient for Klosterman purpose, but in fact, Klosterman was able to obtain a non-trivial bound for this sum. Instead of proving that this sum of q term is bounded by q, he proved that it is bounded by q to the 3/4 by a very elegant argument. And so this was sufficient to solve his problem, which was to give an asymptotic formula for the number of representation of an integer by this degree 2 homogeneous polynomial. So, and about this Klosterman sum, were studied in a broader context by the algebraic geometer André Weil. And I will do the thing shortly because I'm approaching the end of my talk. So what André Weil by developing method from algebraic geometry over finite field and proving what is called a version of the Riemann hypothesis, he was able to improve Klosterman bound by a significant amount. So he proved that the sum of length q, which was here, he proved that instead of the trivial bound q, he proved that it was bounded by square root of q. So he won a square root of q over the square root of the number of terms compared to the trivial bound. And this one was done through techniques from algebraic geometry over finite fields. And in fact, Weil proved a lot of other bound for similar sum. And but all these sums were summed in one variable. And to generalize this kind of bound, he formulated a very important set of conjectures called visionary conjecture, called Weil conjecture. And the question was the problem of counting points for polynomial equations over finite field, but within many variables. And so then this conjecture of André Weil, they were studied in depth by Alexander Grothendieck and his students. And on this occasion, Grothendieck introduced various refounded, in fact, algebraic geometry and invented the so-called étale and the L-adic cohomology. And he developed the theory. And in the end, Pierre Deligne, so Grothendieck's student, also, so using this method from L-adic cohomology, but it is important to note using also arguments coming from really true analytic number theory. the so-called Rankine trick. So Pierre Deligne proved completely the Weil conjecture. And in particular, an application of this Weil conjecture was that you could generalize the bound for Klosterman sum to hyperclusterman sum in the shape of this bound. So these hyperclusterman sum of order k are bounded just by k. So if you go back to the sum of divisor function over arithmetic progressions, then you can use Deligne's bound here. And what you find is that this secondary term is smaller than this main term as long as q is bounded by x to this power, so 2 over k plus 1. Okay, so let's look at what happens. If k is equal to 2, then the exponent is 2/3. So 2/3, you see that here you have beaten the exponent 1/2 that you would get from the Bombier-Rivinogradov theorem, and by quite a lot, by 1/6. And if you take k is equal to 3, then your exponent becomes exactly 1/2. That is the Bombier-Rivinogradov exponent. And if you increase k, then things degenerate, so you get at 2/5, and you are below 1/2. But for us, the important case is k is equal to 3. So because in the work of Zhang, the case of ternary divisors in arithmetic progression happens to be crucial. And in fact, what is crucial is to beat this exponent 1/2 in the case of this exponent d3. And in fact, this is a result that existed already in the 80s. John Friedlander and Henryk Iwaniec were able to pass 1/2 for this ternary divisor function in arithmetic progression. And so they obtained this exponent 1 over 231 plus 1/2. So they passed a little bit 1/2. And so to pass this Bombier-Rivinogradov theorem, they had to use bounds coming from for higher dimensional exponential sum, which are due to Birch and Bombieri, and used Deligne solution of the Weil conjecture. So in the end, so this work of Zhang eventually, by a very clever series of arguments of Zhang and twist, eventually boiled down to this work of Friedlander-Iwaniec, involving this hyperclusterman sum KL3. So what I should say is that with Etienne Fouvry and Emmanuel Kowalski, we revisited the work of Friedlander-Iwaniec to put it in a more conceptual framework. And so using in a way the fact that this ternary hyperclusterman sum of order 3 is a trace function, we could improve the exponent of Bombieri Friedlander-Iwaniec to 1/2 plus 1 over 47. And this ingredient, this improvement of this exponent, of course, it translated into an improvement of Zhang constant. You need over improvement over Zhang's work, but it resulted in this Zhang constant being equal to 5,000. And this is this version of what I would call the modern analytic number theory. So I will finish quickly, but just I want to say, so here I plan to explain what are these trace functions and what are their properties, as you can see. And so, but maybe I should finish with a few things. So in this business involving analytic cohomology and application of these methods from what we call applied analytic cohomology to problems from analytic number theory, really, we should acknowledge a crucial influence of the work of Nick Katz, who is a Will doctoral advisor, and his many books, which were so clearly written that we could use the result for our own purpose of analytic number theorist. And so so Katz put analytic cohomology into, I would say, the real world application, which are application to analytic number theory. And finally, so you won't be too surprised, Will being a student of Nick Katz, but we became in contact where when we met a problem involving analytic number theory and analytic cohomology. And so Will so explained us how to solve the problem, and this is the way we started this collaboration. And just I mentioned one result that so these are pictures by Will and Emmanuel Kowalski involving trace functions. So very nice pictures. And just so just to finish quickly without further explanation. So here is an important and difficult result that we proved about hyperclusterman sums that really used in the full expertise from Will. So just to finish is that, yeah, we have really greatly benefited from Will input and insight into the world of analytic cohomology. But also maybe what this prize shows is that Will got something in return, and maybe the taste to work on problem from analytic number theory. And with his mastery of analytic cohomology, he was able to push back all several techniques from analytic number theory into the world of algebraic geometry, and in this way he made great headways and advances. Okay, thank you very much. I'm sorry I'm over time, but this is usual with me. Thank you.
Well, first of all, Professor Michel, that was a magnificent lecture. I'm very glad that you emphasized these great landmark results on distribution of primes in arithmetic progressions, gaps between primes, and so on, because one needs that to gain a full understanding and appreciation of these more modern advances due to you and the Will 7 and various others that are taking place now. One still has to understand it in the context of those results. It was also very nice that you explained the significance of the work of Andre Way in the process, which I hope I'm correct in saying was sort of like a prototype where great results unproved yet in classical number theory are, so to speak, provable in the context of finite fields. And that is, of course, one of the big things that is happening in this big project of Will 7, but that looks like one of the prototype major results because that concerns the Riemann hypothesis. So thank you so much. Now, Uma Maheshwari in a chat mentioned a couple of questions. Uma, would you like to convey those questions to Professor Michel, or would you like me to read them if you from the chat?
We can do it either way. So there are a couple of questions. One of them is, will you please name a few classes of Diophantine equations where such congruences are used?
Yeah, so this local global principle, it's used a lot for equations which are connected to algebraic groups. And in fact, these quadratic this quadratic equation, sums of squares, and so on, are connected to orthogonal groups. And there you have forms of the local global principles. There are other class of problems in which the local global principle exists, but the proof is less clean in the sense that it does not directly involve this big symmetry provided by the underlying group, but you can manage, and this is what is called the circle method. So the circle method is really a very general technique to establish local global principle in situation when you don't have a lot of symmetry, when you don't have an homogeneous space. And in fact, Will has another series of great work with Tim Browning. So also establishing, so developing the Hardy-Littlewood circle method. So over function fields, but also over the rationals. He has a wonderful average result with Browning and Le Boudec on conjecture of Poonen regarding this local global principle. So yeah, when you have a lot of symmetries, when you can involve an algebraic group, this occurs, and it connects with automorphic forms also. And otherwise, you have other techniques coming really from the circle method.
Thank you, Professor Michel.
One more question.
Yes, this is actually two in one question. Is the Riemann hypothesis connected to some real eigenvalues of a Hermitian Riemann operator? And if so, what are the criteria to such a Hermitian operator to exist?
Okay, so this I have no idea. It is a speculation which has yeah, I have no idea whether this really such operator exists. People have postulated that it exists, and then have extrapolated this existence by creating the random matrix model to make prediction about the distribution of zeros of L function. And this is what I like to call the Katsarnak philosophy, after Nick Katz and Peter Sarnak, who have really studied this possible connection in great detail, and have provided evidence for it, but there is no direct construction. It's more two analogy, which so far, two lines of thought, which so far remain parallel and cross only indirectly.
Thank you. Professor Aladi, there are a couple of more queries. Do you want me to read them out too?
Let me take a look, because it's time now for Professor Matomaki to start. So, yeah, perhaps we can do one thing. If we will probably give, if Professor Michel wouldn't mind sharing his email address, maybe they can send him an email with these questions. Is that okay?
Yes, and maybe we can add these at the end of the session if you have any more queries.
Yeah, or if there is time at the end of Professor Matomaki's talk. But meanwhile, why don't you do one thing, Ms. Uma Maheshwari, in response to the chat, just give them, give this person who asked the question, Professor Michel's email address.
Sure, I'll do that.
Then they can contact you.
I would like to tell Michel that your talk is most loved. There are so many people who have posted their thanks for such a wonderful talk. So I would like to thank you on their behalf. I posted one such nice comment on the chat box too. And there are quite a lot that are actually going on in the YouTube. So thanks for inspiring many people. And I think we will reserve some questions at the end, maybe.
Okay.
So thank you, Michel. Thanks again. Yeah. Can we now proceed to Professor Matomaki's talk?
Yes, sir.
Okay, so let me introduce Professor Matomaki. She is actually one of the most powerful young analytic number theorists in the world today. She was the winner of the 2016 Shastra Ramanujan Prize, which she shared with Maxim Radziwill for the revolutionary collaborative work on multiplicative functions in short intervals, which also shocked the world. Just as Will Saven shocked the world, Radziwill and Maki shocked the world by going well beyond what could be proved previously, even assuming the Riemann hypothesis. And it actually opened the door for many breakthroughs, including progress on the Erdős discrepancy problem and the famous conjecture of the Indian mathematician Sarvadhaman Chawla. The work for which she got the prize, I want to just take 1 minute to talk about it, was especially in connection with what is called the Liouville lambda function, which takes values 1 and -1 on integers with an even number of prime factors and an odd number of prime factors. The equidistribution is related to the prime number theorem, and stronger statements on this equidistribution are even connected to the Riemann hypothesis. And the revolutionary work was on such equidistribution in short intervals, as I said, which vastly improved on earlier results. Professor Maki hails from Finland, and when she finished her master's at the University of Turku in 2005, she received the Ernest Lindelof Award. Lindelof, of course, is a very famous Finnish mathematician whose work is connected also with the Riemann Zeta function. And then after completing her PhD at the University of London in 2009, she returned to Turku, where she has been since as an academic research fellow. It turned out that in 2016, Professor Maki could not visit Shastra University due to a very pleasant family reason. It was not anything serious, but something very pleasant, but that she couldn't come. And therefore, we are actually very pleased that she consented to give this talk on Zoom today. So this is really the first talk she's giving for Shastra University, and it's entitled Siegel Zeros, Twin Primes, the Goldbach Conjecture, and Primes in Short Intervals. Professor Maki.
Thank you very much for the nice introduction. It's indeed nice that I finally get a chance to give a talk here in 2016. My daughter was like 10 months old and I couldn't travel with or without her. So that's why I didn't come then. But now I'm giving a talk. So I will talk about Siegel zeros, twin primes, Goldbach conjecture, and primes in short intervals. And this is joint work with Jori Merikoski, who was my student and who is now a postdoc in Oxford. Okay, but let's start with the basics with the primes. So I write blackboard P for the set of primes, so numbers, natural numbers that are greater than 1, that are only divisible by 1, and so 2, 3, 5, 7, 11, so on. And the letter P will always be a prime here. It is known how many primes there are. By the prime number theorem, the number of primes up to x is about x over log x. And informally, the prime number theorem says that the probability that an integer n is a prime is about 1 over log n. So that's the density of primes around n is 1 over log n. And for this and some more technical reasons, it's convenient that we normalize primes p by log p. So we give them the weight log p. So we write lambda n for the von Mangold function, which is defined to be log p if n is a power of prime p and 0 otherwise. But we never have to care about the prime powers. We can just think that this is giving a weight log p to the primes. And now the prime number theorem is equivalent to the fact that the average value of the von Mangold function is 1, because the density of primes is 1 over log n, and we are now giving them the weight log p. Okay. And then from primes, we get to twin primes. The famous twin prime conjecture says that there are infinitely many primes p such that p plus 2 is also a prime. So an example is 17 and 19 are both primes and differ by 2. And in the previous talk, Philip mentioned that we by now know that there are infinitely many primes that differ by 240. The concept is a strong assertion that there are infinitely primes that differ by 2. And by probabilistic model, one expects that the density of the twin primes is about 1 over log squared, due to the density of primes being about 1 over log x. And more precisely and more generally, one can make a quite precise conjecture about the number of twin primes. So if we look at the sum of up to x of one magnitude function at n and one magnitude function as n plus h, we expect that it's about x times a singular series, which looks like about like this. And if we take h to be 2, then we are counting twin primes the weight log n squared, essentially. And in case h equals 2, this product is empty, so we get this twin prime constant here. And of course, if h is odd, then we really don't have about anything here, because almost all primes are odd. And if we take two numbers whose difference is odd, then one of them is even and one of them is odd. So the even one is most likely not being a prime. So that's why in the singular series, we have the indicator function of h being divisible by 2. And here, if one looks at the singular series more carefully, one sees that it's about of size h over the Euler phi function of h, where the Euler phi function is the number of integers up to n that are co-prime to n. But basically, it's a bit larger than the constant. And if h is, say, a prime, then it's p over p minus 1. So it's about a constant. And before talking more about primes, let me introduce a main thing in the analytic number theory, which is the Riemann function. So for s, real part of s greater than 1, we define the Riemann Zeta function by the series of sum of 1 over n to s, and it can be written as an Euler product, and by the summation formula for the geometric series, also in this form as a product over 1 minus 1 over p to s to minus 1. And the Zeta function can be analytic continued to the whole complex plane, except that there is a pole at s equal to 1. And as already Philip discussed some things about zeros of Zeta functions or L functions, the non-trivial zeros of zeta are the zeros that have real part between 0 and 1. And the famous Riemann hypothesis says that all of them have real part of s equal to half. But this is far from being established. The best we know that is that the so-called Vinogradov-Koborov zero-free region that zeta s have no zeros, where the real part of s is at least 1 minus a constant over log to power 2 over 3 plus epsilon. So even we don't know that there is a small fixed region from 1 minus epsilon to 1, where we don't have a real part of a zero of zeta function, but at least we have some sort of zero-free region. And so how are the zeros and the primes related? Actually, there's a close relation between the zeros of the zeta function and the numbers. In particular, the prime number theorem, which was saying that the number of primes up to x is about x over log x, is equivalent to the fact that the Riemann Zeta function doesn't have any zeros with the real part of s equal to 1. And this zero-free region here gives the best known error term for the prime number theorem. And on the other hand, the Riemann hypothesis is equivalent to the fact that we have a very good error term in the prime number theorem, that the number of primes up to x is about a logarithmic integral plus an error term where we have about square root cancellation. But if we look for twin primes, then actually Riemann hypothesis is of no use. We don't, even if we assume Riemann hypothesis, we can't prove the twin prime conjecture. Actually, I don't think there is a reasonable hypothesis that implies twin primes at all. But there is an unreasonable hypothesis, a hypothesis that we don't believe to be true, which does imply twin primes, and I'm going to talk about that in a minute. But before that, I introduced Dirichlet characters. Actually, Philip introduced them as well, but he did it in a bit different way, and I will do it. So let me do it again, so that if you are not familiar with them, you get an definition again. So we get chi, function from z to z, to be a Dirichlet character of modulus q, and that means that it's periodic with period q, so that chi at a plus q always equals chi a for any a, and it's completely multiplicative, so that chi of mn always equals chi m times chi n, and it is 0 whenever the GCD, this is the GCD of R and Q, is not equal to 1. So if there's a common factor of R and the modulus, then it's 0, and actually it's 0 if and only if this holds. And there's a trivial character, keynote n, which is just the characteristic function of n and q being co-prime. It satisfies all these things because this condition only depends on n mod q. And on the other hand, for instance, the only non-principal, non-trivial character mod 4 is defined at primes by being 1 if p is 1 mod 4, it's -1 if p is 3 mod 4, and it's 0 if p is 2. And by multiplicativity, this can be extended to all numbers, and this satisfies these conditions for a Dirichlet character. And for each moduli, there are some characters. And why they are useful, again, I'm repeating the previous talk, they are useful because they can be used to spot things in arithmetic progressions. That's one reason why they are useful. If we want to spot the condition that n is equal to 1 mod q, then we can write, thanks to the orthogonality of the characters, we can write it as a character sum. Okay, and that leads us to the Dirichlet L functions. So for a Dirichlet character chi, the corresponding Dirichlet L function is defined similarly as the Riemann Zeta function, except that in the numerator we have chi n instead of 1. So it's the sum of chi n over n to s. And it can be again written as an Euler product of values of chi p, and in a short form of an Euler product like this. And these Dirichlet L functions have a very similar theory as the Riemann Zeta function. In particular, we had the generalized Riemann hypothesis, which asserts that all the zeros of the Dirichlet L functions have real part of s equal to half. But for the Riemann Zeta function, we had this nice zero-free region, but in this case, one hasn't been able to rule out the possibility that there is a real exceptional character which has a real zero very close to s equal to 1. So this zero-free region doesn't hold. And so that's sort of the main assumption we are making this time. We are looking at this sort of alternative world. What about if this Ziegler zero exists? What if we have an exceptional zero which is very, very close to s equal to 1? Nobody believes that it exists, but nobody is able to rule out that it doesn't. And we want to know what happens, what it tells us about the primes if there was such an exceptional character. And so we say that beta is a Ziegler zero, and we write beta equal to 1 minus 1 over eta log q. If beta is so close to 1 that this eta here is at least 10. So this is what we call a Ziegler zero. And one might ask, why is it interesting to think what happens if we have a Ziegler zero if nobody believes that there is a Ziegler zero? But in some cases, people have been able to prove a theorem by dividing into two cases. They first prove it if there is a Ziegler zero, and then they prove it if there is no Ziegler zero. So sometimes it might be useful. And also it tells us something about the relationship between L functions and zeros and primes if we get a theorem about what happens if we have a Ziegler zero. Okay, but let me make a non-serious sidetrack before we go on. So I have been giving some talks about primes, and I have described how Legos are like primes. So for instance, if we have that sum of 1 over n diverges, then so does sum of 1 over p. So we can take the Lego bricks as primes and the buildings as integers, and then analogous, if the number of buildings is tending to infinity, like the integers, then also so must the number of bricks. So like the number of integers tends to infinity, then so must the number of primes. But one can ask, can one relate these exceptional characters to Legos? What's the relationship here? And yes, here you can see it. Here I have the imaginary axis and real axis, and all the ordinary characters are standing very neatly on the half line, the real part of s equals to half. But then we have this one exceptional character which insists to stand very close to the s equal to 1 point here. But usually this sort of characters don't exist. Okay, so let's go back to the actual real secret zeros. So we write beta for secret zero, and what do they imply about twin primes? There's a result from Heathrow about 40 years ago, where he saw that actually if there are secret zeros, then there are twin primes, and he established the expected asymptotic formula for the, more generally for the von Mangold function twisted by von Mangold function at n and n plus h. So case h equal to 2 corresponds to the twin primes, and because this is then a constant times x, and as soon as eta tends to infinity, this error term is of small order. So as soon as there is a secret zero with large eta, zero very close to s equal to 1, there are infinitely many twin primes. Or, well, one needs several secret zeros because each secret zero gives only about finite amount of twin primes. But anyway, secret zeros imply twin primes. And then there was a very recent paper by Teresa and Joni Teräväinen that they improved this quantitatively. Heath-Brown gets an error term x over log eta, and Tao and Teräväinen got rid of one of logs. They get an error term x over log to 1 over 20 eta. And actually they considered also a more general case that you have Liouville functions here as well. They consider the sort of Hardy-Littlewood over conjecture. And my work with Jori Merikoski gives an improvement of results of Heath-Brown and Tao Teräväinen. So Heath-Brown had log eta and Tao and Teräväinen had log eta, but we have a more fastly decreasing function here of x minus c square root of log eta. And in part of the range, if we have that x is at least q to like 10 log eta, then we actually have a polynomial saving here, like we get like x over eta type error term here. Okay, so we get, it's a corollary of our main theorem that we get an improved error term for the, so we know more precisely how many secret zeros there are under the assumption. And there is, in the title, I promised to talk about twin primes, about the Goldbach conjecture, and about primes in almost all short intervals. So let's turn to the Goldbach conjecture. So the basic form of the Goldbach conjecture says that every even integer, at least 4, can be written as a sum of 2 primes. So for instance, 10 is 3 plus 7, or 20 is 13 plus 7, and so on. And like for twin primes, there is an expected asymptotic formula for the number of representations, and it has the same singular series as the twin prime case or the Hardy-Littlewood conjecture case. And it's the expectation is that the number of representations of 2h as a sum of 2 primes, n1 and n2, is about 2h divided by log squared x times a constant. And there has been some activity about how is this related to secret zeros. And what Jori and I have been able to show is that if a weak form of the asymptotic Goldbach conjecture holds, then there can't be secret zeros. So more precisely, we can show, if we fix any q, we can show that there exists, and delta, we can show that there exists a constant eta, depending only on the delta, such that if we have some even number 2h, which is divisible by q, and which belongs to this wide range, and for which we have that the weak form of the asymptotic Goldbach conjecture holds, so we don't need an asymptotic formula for the number of representations, but it's enough to have upper and lower bounds which are sort of quite a bit off from the asymptotic. It's sufficient to have a lower bound of delta times the expected form and upper bound of 2 minus delta times the expected form. Then we get that there can't be a secret zero of modulus Q. So if a weak form of the asymptotic Goldbach conjecture holds, then there can't be secret zeros. And this improves on the recent result of Friedland and Ivanets, who had to assume this, that the weak asymptotic Goldbach holds for several different even H's that are 0 mod Q. For us, it's enough to have just a single, for a given modulus Q, it's enough to have a single H, 2H, such that we have the Goldbach to rule out the possibility of secret zeros. Okay. And so what we need to do in order to attack both the twin primes and the Goldbach, we have to study sums of this form there. This is the von Mangold function, the primes weighted by log p. And in case of the twin primes, we basically take n to be a plus sign. And in case of the Goldbach, we take the minus sign. Then we look at von Mangold.n and h minus n. And now in particular for Goldbach, we have to have that h has about the same size as x in order to get what we want. And so we have to work uniformly with respect to h. Our error terms here in the corollary, for instance, in our corollary and in all the previous results, the error terms depend on h. But if we want to get a result that is uniform in h, then we can't have this dependency for the error term on the parameter h. And nobody has been dealing with this sum uniformly in h before. And there's something interesting going on when we work uniformly. In particular, we get an additional main term. The conjecture is not anymore true if we assume secret zeros, then we don't get the correct asymptotic for the additive conjectures. So consider the most simple case that causes us trouble, which is h equal to q. So we look at this von Mangold.n and von Mangold.n plus q. So now if there is a secret zero, then it's known that the primes actually are not equidistributed modulo q if eta is large. So then residual classes a mod q, for which chi of a is -1, contain almost twice as many primes as one would expect. And on the other hand, residual classes a mod q with chi a equal to 1 contain very few primes. So there is sort of the primes don't behave as they should in arithmetic progression mod q if there is a secret zero mod q. And given this, this lambda n and lambda n plus q are less independent of each other than they should, because if lambda n is a prime, then n belongs to a arithmetic progression where there are probably belongs to an arithmetic progression. There is a lot of primes, and this n plus q belongs to the same arithmetic progression, which sort of double the chances that n plus q is prime if n is prime. And that's why we expect that actually we don't have originally what the Additive conjecture says, or the general form of twin prime conjecture says that this is asymptotically this singular series times x, but now we get double what it should if there's a secret zero. And our theorem in the general form confirms that, yes, we get this consequence of secret zeros. And for simplicity, I state the theorem here only for q odd, because the main term becomes more annoying if q is even. So we let chi be a primitive character, and we assume that the corresponding L function has a secret zero, a real zero beta equaling 1 minus 1 over eta log q, which is very close to 1. And we get x to be at least q to 10, and we write v for the log x over log q. There are some technical stuff here, but what we get is we get an asymptotic formula for this sum that we are interested in. And now, instead of just having the x times the singular series, we have another term here, which depends on the character value. In the case we are looking at the twin primes, it's just chi plus 1, it doesn't matter. And we get this product here. Now, if say h is 2 or something like that, then this product will be small because it's product of 1 over p minus 2 for everything dividing q. But if q and h have a very large common factor, in particular if q equals h, then this product is empty and the main term becomes x times sigma series times 1 plus chi plus minus 1. So this explains what I said in the previous slide. In particular, if we have that if q and h are equal to each other, then we get double the main term than we should. And also in the case of the Goldbach constructor, when we have the minus sign here, we get either twice the main term or we get a 0 main term. So that's here we see the phenomenon behind the Goldbach. And here we have an error term, don't care too much about it. It just shows that we get quite a bit of saving, but it always works with the v constant, and then we have here 1 over x square root of log eta. That's the worst saving we get from here, and sometimes we save more. Okay, and now this result is uniform in H, and that brings us to the third topic in my title, which is primes in almost all short intervals. So we can get a corollary on primes in almost all short intervals, but let me first tell you what is known about this. So a probabilistic model predicts that if we look at intervals of length h, then there are about h over log x primes in this interval, because the density of primes is 1 over log x. And a probabilistic model predicts that this happens as soon as h over log x tends to infinity with x. And this is known in some cases. So for instance, if one assumes Riemann hypothesis, this is known if h tends to infinity faster than log squared x. So one has to take a bit longer intervals if one just assumes Riemann hypothesis. But here Brown showed that if, in addition to Riemann hypothesis, one assumes the pair correlation conjecture about how the zeros of the Riemann zeta function see each other, then one can get the result predicted by the probabilistic model. And on the other hand, unconditionally, the results are quite a bit worse. One has to look into intervals of length at least x to 1 over 6 plus epsilon in order to get that almost all intervals of this length contain the number of primes. If one is just happy that almost all contain some primes rather than the expected number, then one can get the lower bound for intervals of x to 1 over 20. And what we get is that if we are secret zeros, then we get primes in almost all short intervals. And so again, we have the very same setup as before. We had we assume that there is an exceptional zero, and then we look at a certain range of x's depending on q, and we look at interval length h, which is at least log x, and then we look at the mean square of the short interval average, the number of primes in short intervals weighted by log p, and we compare it with the expected main term. And then we get an upper bound for this. A trivial upper bound would be h squared times x. And here we see that we save something if eta is tending to infinity and if h over log x is tending to infinity. So that's what the probabilistic model predicted us, that we have to have that h tends to infinity faster than log x. And in this case, we get an asymptotic formula that the number of primes in the short interval of length h is about h over log y for almost all y's. And this is actually quite a straightforward corollary of our original theorem, because we just have to square this out and it leads us to the correlations of one Monoid function at n and one Monoid function as n plus 8, and we have to sum them up. Okay, Let me explain then why is it helpful to have a secret zero? Why can't we prove all these fancy theorems like twin primes and Goldbach conjecture if we have secret zeros? Why is it helpful? But before doing that, I have to introduce another function, which is the Mobius function. And Mobius function is a multiplicative function, which is -1 at primes and 0 at prime powers. So in other words, the Mobius function at n is -1 to k, if n is a product of k distinct primes, and Mobius function of n is 0 otherwise. So if there's a repeated prime factor, it's 0. And one more piece of notation is the additive convolution of two functions. I write not additive, a convolution of two functions f and g. At n is the sum of all divisors of n. I mean, I write n as a times b in all possible ways, and I take f a and g at b. And now if we look at the convolution of mu with the constant function 1, we get that it's the sum of n equaling ab of mu of a, and it's the same as sum of d dividing n mu d, and it's actually the indicator function of n being 1. And this can be seen by an inclusion-exclusion from the definition here, and it's called the Mobius inversion. And this can be written also in terms of Dirichlet series, 1 over zeta s. Zeta s had the Euler product that it was the product of 1 minus 1 over ps to -1. So 1 over zeta s is the Euler product 1 minus 1 over ps. And multiplying this out, one sees that it's the sum of Mobius function over n to s. And similarly, 1 over ls chi is the sum of Mobius function chi n over n to s. And Mobius function is very closely related again to zeros of zeta, because the Dirichlet series having the Mobius function here has a pole at all the zeros of zeta and so on. So this actually Mobius is very closely related to the primes. Okay, so recall that the Mobius function was defined to be -1 for all primes, and that the convolution of Mobius function with 1 was the indicator function of n being 1. And now, why does it help if we have an exceptional character? Now, if we have that L beta chi is 0 with beta close to 1, then by continuity, we know that L1 chi must be exceptionally small. And so 1 over 1 chi must be exceptionally large. And by the Euler product formula, we can write it as the product of 1 minus chi p over p. And now if this thing here is large, it means that the chi p must be -1 quite often. And now this means that chi behaves like Mobius function, because Mobius function is always -1 at primes. And we got that the chi p is -1 at primes, at least most of the time. And this means that consequently, if we look at convolution of 1 with chi, it's about the same as the convolution of 1 with mu, and it vanishes often. And so we can get an approximation for one Magnot function. This is, I'm waving my hands very much, but I will give some more figure in the next slide. But here we have for the one Magnot function, we can represent this as a convolution of Mobius and log. This is a well-known fact. And by definition, this is the sum of n equaling km mu k log m. And now if we think that chi behaves like Mobius, we can replace the Mobius here by the chi. So we get an approximation to the one Magnot function as the sum of, as the convolution of chi and log. And now when the modulus of chi is small compared to n, this right-hand side here sort of has a similar complexity as the divisor function tau. And so unfortunately, this is not the Ramanujan tau function, it's the divisor function, even if we are in the Ramanujan conference. And this is a significant simplification compared to studying the one Magnot function. It's much easier to study a convolution like this, where we have two low complexity functions. Log is a smooth function and chi k has a small modulus. And such ideas have been extensively utilized by Friedland and Ibanez. They are calling this an illusory sieve when you sieve assuming that there is secret 0. Okay, so let's make that approximation more rigorous. And for that, we write lambda for the convolution of 1 and chi, and lambda prime for the convolution of chi and log. And so we can write lambda convert with 1 mangled as 1 convert with chi from the lambda and mu convert with log from the 1 mangled. And now we can rearrange this as the convolution of 1 and Mobius and the convolution of chi and log. And now remember that this is just the indicator function n being 1. So the convolution of it with something is just the something, which is chi as log, and it's lambda prime. And by the formulas here, we can see that lambda and lambda prime are both positive, which is actually not relevant at the moment. But anyway, this allows us to write lambda prime of n as the convolution of 1 mangled and lambda. And by definition, this is a sum of n being km 1 mangled k lambda m. And now we take out the term with m equaling 1, which is simply 1 mangled of n. And then we are left with the remaining terms where m is greater than 1. So in the previous slide, I said that 1 mangled of n can be approximated by lambda prime of n, and now we have an error term for the approximation. But this is not very convenient because m's here might be quite small, so we make a little trick before we proceed. So we take z to be x to 1 over u with u quite large, and we write pz for the product of all primes up to z. And we multiply both sides here by the indicator function of n being co-prime to pz. So we only consider n's whose all prime factors are at least z. So doing this, we get to the left, we get the lambda prime n times the indicator of n having all prime factors greater than z, and the same thing for the 1 mangled function, but note because 1 mangled function is supported on prime powers, this doesn't really affect the 1 mangled function. And then in the last sum, we also get this condition that Lm is co-prime to pz. And now the good thing about this here is that because we know that m is greater than 1, and it doesn't have any prime factors that are smaller than z, this sort of forces that m must be at least z, and also L must be at least z. And so this means that we have a real bilinear form here, which makes things easier. And this setup is the same as my co-author's Jori Merikoski's in his recent work, where he proved that if there are secret zeros, then or actually if there are exceptional characters in some other sense, there are infinite many primes of the form a squared plus b to 8. Okay, so what we want to do, we want to study this sum of 1 mangled function at n and 1 mangled function at n plus 8, this shifted convolution sum. And in the previous slide, we got this formula for the 1 mangled function. Just don't care about us being restricted numbers that don't have prime factors smaller than z, because we are essentially looking at primes, so it doesn't matter. And now we replace both 1 mangled functions here by this approximation here. And the first term, this lambda prime, is what gives us the main term, whereas the second term contributes little. And this is because we think that our approximation is good. We wanted to approximate 1 mangled by lambda prime, and we think that this approximation is good. And it's good because lambda m was the convolution of 1 and chi, and we expected that chi behaves like the Mobius function, which makes lambda to vanish often. And we can indeed get an upper bound for a sum of lambda m over m. I don't want to explain this upper bound in the detail, but anyway, it's a good upper bound for the sum, showing that lambda m actually vanishes often. Okay, so let's do this replacement of 1 mangled functions by lambda primes. So we use this formula that 1 mangled function is approximated by lambda prime times the indicator of n being co-prime to pz minus cn, where cn was this bilinear form here. And now we want to replace in this sum up here, we want to replace the one monoid function by lambda prime. And this gives us an error which is Cn times one monoid function at n plus h summit. And using the definition of the Cn, we can write it in this form. Just rearranging a bit. Okay, this should be z less or equal to m here. And for the thing on the right, for the sum over L, we can give an upper bound of the correct order of magnitude. It's about x over m times h over phi h. And then we encounter sum of lambda m over m. And in the previous slide, we had an upper bound for it. So we get that we can do this approximation. I don't talk more about the details, but just you can take it for granted that we can make this approximation of replacing one monoid by lambda prime. And similarly, we can replace the one monoid at n plus h by lambda prime n plus h. And now if we use the definition of lambda prime as a convolution of chi and log, then we get a sum like this. We replace this by m1 n1 and this by m2 n2 and get the chi's and logs appearing. And now this roughly corresponds again to having a divisor functions, because chi and log n are both of low complexity. And this would be not too difficult, but one has to be careful to deal with this sum. And we split into cases according to the sizes of m1 and m2. I don't go into details about this, but we look at m1 and m2 being either smaller than x to half or greater than x to half. And because there are two variables, there are four cases. And so in order to deal with all these four cases, we prove the general proposition which concerns some for this form with a general smooth weight, because sometimes we have log somewhere in the larger variable and sometimes in the smaller variable and so on. I don't want to discuss this thing too much because it's getting a bit too technical. But the point is that we can give an asymptotic formula for very general sums like this. And that there are certain terms that we have to deal with. There's a complete character sum, mod q here, that we have to deal with. And there are sums over m1 and m2, but we don't have a relation between m1 and m2 or n1 and m1 here anymore. So these things are easier than the original sum, where we had this annoying condition that m1 n1 plus h equals m2 and n2. So in particular, understanding this sum of lambda prime n plus h that we wanted to understand reduces to understanding things on the right hand side. These products are easy to understand, but there's a character sum and then there are some other terms. So we have this character sum and then we have sums of chi m over m times log m or log y over m. And to deal with the second thing, we again use the fact that chi approximates mu or Mobius function in case we have a secret 0, and then we can replace chi by mu, and we can use some standard techniques to solve an asymptotic formula for this. And for the character sums, we can evaluate them exactly because they are complete character sums and we have a quadratic character. It's not too complicated to evaluate the character sum. And now we can see that this term where we have the non-trivial character and the trivial character, we get the contribution of size 1 over q, which is small, but here we have a contribution of size a phi h or h over phi h. And here we have a similar thing, but now we have a product of 1 over p's, which is sometimes it's small, but now in case say h equals to q, if our shift is divisible by q, then this product at the end is empty and this product is empty. So we get exactly the same term from both character sums. And that sort of explains why we have the secondary main term in the case that h and q have a large common factor. We get the main term also from this case where we have the non-trivial character. Okay, so that's was the proposition that get us to the need to deal with the complete character sums and these sums, and I showed how we can deal with this. And let me say like 3 lines about the proof of this proposition. So first, we have to spot the conditions that we want things to be co-prime to Z, and we use the beta sieve to do this. The previous authors have used the Selber sieve, and it gets quite messy. And I think this is the reason we actually improve on the error terms, is that they prove some more messy than ours. And so they couldn't see so easily where the worst error terms come from. I quite believe that one could get the same error terms by Selber sieve if one worked carefully, but with the beta sieve, it's just easier. And after detecting these conditions by 3 applications of beta sieve, we write this shifted convolution condition here as M1 being equal to H times N1 inverse mod M2, and then we use Poisson summation. And then from the Poisson summation, the sort of k equal to 0 gives the main term, and the error terms are handled by the well bound, because there we get incomplete Kusterman sums. And so eventually, combining everything, we got this main theorem, which said that we can deal with this Sound von Mangold function, and as corollaries, we get these results about twin primes and Godbach conjecture and primes in almost all short intervals. So if we had Siegel zeros, then wonderful things would happen, but nobody believes that there are Siegel zeros, so we don't have actually these wonderful things. Okay, thanks, that's all I wanted to say.
Thank you, Professor Matamaki, for a very nice talk, which actually was thorough in the details. And I really appreciated the description of not only the Siegel zero side, but also many of the things from the sieve side. So thank you so much. We have time for questions. So I'm going to ask Mrs. Uma Maheshwari if she can share these questions with the speaker.
Yes, there are a couple of questions. So one from Dr. Kannan on any specific property of Mangold function here?
So I'm not sure at what point this question was asked, but
this was during the earlier.
I think when you first defined the von Mangold function to set the thing, I don't know whether when you say he wants a specific property of the Mangold function in relation to what? Did he say it?
No, the question is only on this, and there is no further.
I think maybe the question, if I can understand, because I saw it when it first came up, Kaiser, when defined when you said that the density of primes is 1 over log n for a given integer, in the neighborhood of n, and then you introduce the von Mangold function to get the sum to be x. I think the question he asked was why specifically that form of the weight which will give this x. Why, so maybe I don't know. So why specifically does the von Mangold function play such a convenient role in this? I think it's the sum of that is log n.
Yeah. So it's for convenience that one wants to use the von Mangold function, because the generating Dirichlet series is zeta prime over zeta. So that's more convenient than using the characteristic function of primes, which is the Dirichlet series involving log of zeta and things like this. So that's why we want to use
the very convenient property that the sum of the lambda d's over d dividing n gives you log n.
Yeah.
Which is, of course, a smooth function. Log n is smooth. So this is a summatory function. So it's very convenient to deal with it.
Yeah, it's true.
That I think is the answer to Professor Kannan. The second question, please.
Yeah, so this is about Siegel zero case, where the viewer has posted a question as you mentioned, for Siegel zero case, the residue classes A mod Q with x of A equal to -1 would create twice that of expected. Will it be more than that of double in all residue classes?
So in all residue classes, the chi of A is -1. We get twice as many primes as we expect. and half of the residue classes satisfy this. And in the other half of the residue classes satisfy that chi of A is 1. And in these residue classes, we don't really have almost any primes. There are very few primes. So the total number of primes is the correct, but half of the residue classes is having twice as many as they should, and half of the residue classes are having very few primes.
Okay. Thank you. So there is one more query. Actually, it's 2 in 1, I guess. How many large and small gap of twin primes found so far?
I think it's a numerical question that's being asked. Let's say up to 5 million or whatever. Any data is what is being asked, I think.
Yes, and there's another part of the question. At the end of the talk, could you also explain in terms of Riemann zeta function?
So the Riemann zeta function doesn't have an exceptional 0, so we don't have sort of a relation with these things with the Riemann zeta function. And as for the twin primes, there's of course numerical evidence that the expected asymptotic formula holds, but there is no proof. But people have been calculating, and it looks like the expected asymptotics is correct.
Right. I don't see any more queries coming up here, and people are happy with their answers. They've said, yes, got it. That's good.
So should we conclude the session by thanking Professor Maki? Do you have any comments?
I think.
All right. So if there are no more questions, I would like to thank Professor Maki for a very lucid talk. It's not easy to give these talks which have such technical details, but I think she managed it very well. Thank you so much. We have 2 talks tomorrow. Ramanujan's birthday. That is when I think the second lecture is by Professor Savan, and the first lecture is by Professor Ken Ono, who has been a regular at the Shastra conferences for the past, ever since the conferences were launched. So we have 2 very fine lectures tomorrow, and I look forward to seeing all of you, not only the Zoom persons, but those who appeared in YouTube. I hope you'll enjoy the talks tomorrow as well as you have enjoyed the talks today. Thank you so much. And thanks to the Shastra organizers and Uma Maheshwari for the arrangements both on Zoom as well as on YouTube.
Thank you very much. And I'm sure that it will inspire all the youngsters. There were a lot of students, and many of them have posted their thanks because they have understood several nuances. It was very technical, but I'm sure they have got introduced into this wonderful world. So thanks.
But Uma, is it possible for our 2 speakers to be able to see those comments?
I can post these.
Because some of them have expressed their appreciation. It would be nice for them to.
I would like to. I would do that. I would do that.
Yeah. Okay. But is that available only while we are together live, or is it something they can see later in YouTube?
I think it should be possible to see it later too, because the comments would come on as chats.
Okay. All right.
Yeah.
Okay, that would be good because they would appreciate the feedback.
Absolutely.
Yeah. So thank you, Philippe, and thank you, Kaisa, for your 2 lectures. And again, as I said, we look forward to Will and Ken's talks tomorrow. Okay.
Thank you very much. Bye-bye.
Bye-bye.